Very good morning to one and all. So we were discussing about the pneumatic and hydraulic actuation systems. So the hydraulic or pneumatic cylinder is an example of a linear actuator. So while we are discussing the pneumatic and hydraulic actuation systems, I told you there are mainly two types of actuators we can say. Yeah, that is a broad classification: linear actuators and rotary actuators. So the hydraulic or pneumatic cylinder is an example of a linear actuation system, or it's a linear actuator. And if we look at the principles or the construction, so that is same for both hydraulic and pneumatic versions, and the differences between these two in terms of the size. I mean, you know that the high pressures are used with the hydraulics. Now, usually, if it is a hydraulic cylinder on a pneumatic cylinder, both consist of a cylindrical tube along with a piston or ram which can slide inside it. Now, the cylinders are classified into two: single acting cylinders and double acting cylinders. Now, what is meant by single acting cylinders? The term single acting is used when the control pressure is applied to just one side of the piston. Now we use a spring often to provide the opposition to the movement of the piston, I mean the reverse movement. And you may please note that the term single acting is used when the control pressure is applied to just one side of the piston. Now usually the other side of the piston is open to the atmosphere. Now if you look at this diagram, you can see that it's a single acting cylinder with a spring return. Now if you look at the diagram, you can see the different parts. The spring piston, you can see this is through the fluid enters, fluid exit, piston rod, and this is the one symbol corresponding to this single acting cylinder. Now if you look at the diagram, the fluid is applied to, I mean the fluid pressure is applied to one side of the piston. Suppose here, as it is here, the fluid is applied to one side of the piston at a gauge pressure P, with the other side being open to the atmosphere, or so the other side being at atmospheric pressure. So it produces a force on the piston, which is equal to gauge pressure P into A, where A is the area of the piston. So the fluid is applied to one side of the piston at a gauge pressure P, with the other side being at atmospheric pressure. So produces a force on the piston of PA, where A is the area of the piston. Now what will so this is actually the theoretical force, the force acting on the piston. What would be the actual force? Of course, there will be friction involved. Because of the friction, the actual force will be less than the theoretical force. Yeah, the actual force acting on the piston rod will be less than this because of the friction. Now, what is meant by, so what is shown here is the control of a single acting cylinder with no current through the solenoid and a current through the solenoid. Now you can see, look at the second one. Yeah, actually, and if you read this diagram, you can see that this is a symbol for a pressure source or pressure inlet source. This is a symbol for exhaust. Now look at the second diagram. I mean, when the current passes through the solenoid, the valve switches position, and the pressure is applied to move the piston along the cylinder. You can see it. Okay, so when the current passes through the solenoid, the valve switches the position and the pressure is applied to move the piston along the cylinder. Now when the current through the solenoid ceases, this one, you can see that because of the spring action, the valve reverts to its initial position, and this air which is sucked here is vented from the cylinder through this exhaust. And this is how a Asyn Lec cylinder works. Now, so we see Asyn Lec. So what is meant by double acting cylinder? The term double acting is used when the control pressures are applied to each side of the piston. You can see a double acting cylinder here. Look at the nomenclatures which they have pasted. And right side you can see the valve symbol too. All of you should learn this symbol, etc. And here you can see the two lines drawn which indicates the control pressures are applied to each side of the piston. This side as well as this side. Okay, so the difference in pressure between the two sides that results in the motion of the piston. Okay, so that is the difference between a double acting cylinder and a single acting cylinder. Now, if you look at the diagram, sorry, this is the control of a double acting cylinder with a solenoid. The first figure, which is not activated, and the second is activated. Okay, so if you look at the diagram, the current through one solenoid causes the piston to move in one direction, with the current through the other solenoid reversing the direction of motion. Okay, which means the piston has two moments, one is towards left and one is towards right, and these two positions indicate the to and fro motion of the piston. I mean the current through one solenoid which causes the piston to move in one direction, and the current through the other solenoid reversing the direction of motion, that is opposite direction. It is very clearly seen from this diagram. Now, which cylinder and how to choose the cylinder for a particular application? And you may please note that the choice of the cylinder is determined by the force required to move the load and the speed required. Now, um, of course, there will be an end use for this pneumatic cylinder. As we already discussed while discussing the mechatronic design paradigm, the actual job of doing is done by the actuation system. So the cylinder as an actuator, it has to do some work. Either it has to move some load, it has to pick some object, something, isn't it? And how much load is required to move the load? And what is the speed required? How much fast it should move? And that are the two factors which determine the choice of the cylinder. Now you may please note that the hydraulic cylinder are capable of much larger forces than pneumatic cylinders, and whereas the pneumatic cylinders are capable of greater speeds. Now the force produced by the cylinder is equal to the cross-sectional area of the cylinder multiplied by the working pressure, which we already see, the pressure difference between the two sides of the piston and the cylinder into cross-sectional area. Now, for example, a cylinder for use with a working pneumatic pressure of 500 kPa and having a diameter of 50 mm and thus give a force of 982 Newton. Okay, look at the same hydraulic cylinder with the same diameter and a working pressure of 15,000 kPa will give a force of 29.5 kilonewton. Look at the difference. Look at the output which hydraulic cylinder can give. The cylinder with the same diameter, the earlier one was a pneumatic one, this was a hydraulic one. Look at the difference in force produced by these two cylinders. Okay, and again, assume if the flow rate of a hydraulic liquid into the cylinder is the volume of Q per second, then the volume swept out by the piston in a time of 1 second must be Q. And for a piston of cross-sectional area A, this is a movement through distance 1 second, where we have Q is equal to A into V. So thus the speed V of the hydraulic cylinder is equal to the flow rate of the liquid through the cylinder divided by the cross-sectional area. It is very clear, the speed of the hydraulic cylinder. Now we already seen how we find out the force. Now we are looking at the speed. So you can see we have Q is equal to AV, and from that you can find out the speed of the hydraulic cylinder, that is the flow rate of the liquid through the cylinder divided by the cross-sectional area of the cylinder. Thus for a hydraulic cylinder having a diameter of 50 mm and a hydraulic fluid flow rate given 7.53 meter cube per second, and you can find out the speed, isn't it? Q by A is equal to 3.8 meter per second. So here actually the 7.5 into 10 raised to minus 3 meter cube per second. Okay, this is actually erroneously entered 7.5 into 10 raised to minus 3. Sorry for this mistake. So anyway, you can find out the Q by A, you can find out the speed. Now you must please note that the speed of the pneumatic cylinder cannot be calculated in the same way, since the speed depends upon the rate at which the air can be vented ahead of the advancing position. So actually we use a valve to adjust this, can be used to regulate the speed. So what we learned just before is how to determine the speed of a hydraulic cylinder. You cannot find out the same way for a pneumatic cylinder because the speed depends upon the rate at which the air can be vented ahead of the advancing piston. So look at this problem. You have a hydraulic cylinder with you. Hydraulic cylinder to be used to move a workpiece in a manufacturing operation through a distance of 250 mm in 15 seconds. If the force of 50 kilonewton is required to move the workpiece, what is required working pressure and hydraulic liquid flow rate if the cylinder with a piston diameter of 150 mm is available? Okay. So the question you can see that you have a hydraulic cylinder, you need to move a workpiece. That is the actuation you need to do here in this manufacturing operation. You need to move through a distance of 250 mm in 15-second time. You need a force of 50 kilonewton to move this workpiece. Then what is the required working pressure and what is the hydraulic liquid flow rate? We have the diameter of the piston is given. And look at the solution. You know you have the cross-sectional area of the piston. How to find out pi d square by 4? That is pi into what is the cross-sectional area? D square. That is we have 150 mm is given. So 0.15 meter is the diameter. So pi into 0.15 square by 4, you will get the cross-sectional area. Now, the force produced by the piston is equal to the product of the cross-sectional area into working pressure. അപ്പോൾ നമുക്ക് ഇവിടെ force അറിയാം. We have force, that is 50 kilonewton. So now area known. From that you can find out the working pressure, isn't it? That is 50 into 10 cube divided by what do you find out the cross-sectional area. From that you will get the working pressure. Now the speed of the hydraulic cylinder is equal to the flow rate of liquid through the cylinder divided by cross-sectional. Q is equal to AV. So V is equal to Q by A. What is Q here? What is Q? How to find out the Q? So the speed of the hydraulic cylinder is equal to the flow rate of the liquid through the cylinder divided by cross-sectional area of the cylinder. So by this way, you will be able to find out the final answer. Thank you.